Please welcome to the stage SC24 Awards Chair Scott Paikin and SC24 Awards Vice Chair Venkatesh Kannan.
Good morning, everyone. Earlier this week, at the opening session on Tuesday, SC24 recognized Professor David Padua as this year's recipient of the ACM IEEE Computer Society Ken Kennedy Award, Professor William Tang as recipient of the IEEE Computer Society Sidney Fernbach Memorial Award, and Dr. Norman Joupy as recipient of the IEEE Computer Society Seymour Cray Computer Engineering Memorial Award. In this session, each of these three award winners will present a talk on some of their path-breaking advances in computational science and technology.
David Padua is the Donald Bigger Willett Professor Emeritus in Engineering in the Siebel School of Computing and Data Science of the University of Illinois at Urbana-Champaign. He has devoted much of his career to the study of languages, tools, and compilers for parallel computing, leading or participating in numerous research projects in these areas in collaboration with researchers from other universities and industry. Please welcome to the stage Professor David Padua.
Thank you very much, and thanks everybody for coming here this early. So this talk is about high-level compiler transformations, and also about compiler weaknesses. It has three parts. First, we are going to talk a little bit about high-level compiler transformations and their origin back in the remote past. Then we are going to say something about compiler stability as a weakness of today's compiler technology. Compiler technology research has produced a very powerful methodology, but it's not sufficient for compilers to be effective. You need a solid methodology to guide the transformations and decide when to apply them. And in that, there is still a lot of room for advancement. And finally, we'll talk about a couple of strategies to reduce the impact of this instability, which is a manifestation of the weaknesses of today's technology. And by reducing the impact of instability, the hope is to obtain more reliable compilers, compilers to become better tools for optimization, and as a result, the programs to execute faster. So let's start by saying what are high-level transformations. These are those that manipulate the source program at the relatively high level of abstraction. We can say at the level of the abstract syntax tree, or if you prefer, at the source program level. These transformations can operate on all classes of statements, including compound statements like loops and if statements. The goal of these transformations, like all compiler technology, is to improve performance, functionality, or readability, without, of course, changing the outcome of the original program. And also, like all of compiler technology, high-level transformation is not strictly necessary in the sense that all these transformations accomplished can also be done by hand if we are willing to invest the time and transform our programs by hand. So even low-level compiler techniques are optional, since we could very well program in assembly language. Of course, we don't want to do that, because we want to facilitate the task of programmer, applying either high or low level transformations, which will definitely reduce the cost and will enable results that otherwise will be too expensive to achieve. Imagine writing a million-line program in assembly language would be a horrible enterprise. This is particularly true of the complex task of optimizing programs, as we will see in a minute. So next, I'll show you a couple of examples of high-level transformations so we know what we are talking about. The first one is vectorization that converts iterative constructs into vector form. Vector operations, of course, are of great importance, in part because, as Jim Golub, the famous numerical analyst, said, everything is linear algebra. So you can use vector operations for high-performance computing, for machine learning, and symbolic computation also. It's ubiquitous in computer science. So the loop that I am presenting here is quite simple, but in the frequent case of multiple nested loop, vectorization could be quite complex, and there could be numerous ways to vectorize. Programmers typically will have a hard time figuring out which way to choose. Clearly, the usefulness of automatic vectorization increases with the number of statements and the levels of nesting of the loops. A second example is tiling, which transforms a multiply nested loop like this one, a doubly nested loop in this case, where arrays A and B are traversed by rows and columns, into a version like this that traverses A and B by blocks. So basically, in this case, what we are doing is converting array transposition by rows and columns into transposition by blocks. So there are two reasons why I chose to discuss high-level compiler transformations in this talk. First, because I have worked in this area continuously throughout my career since I was in graduate school. And second, and more important, because this was Ken Kennedy's main area of research. The award I received yesterday is particularly significant for me. I knew Ken Kennedy well and very much admired his scientific contributions, and in general, his service to our research community. So most often, compiler transformations aim at enhancing parallelism and locality, but there are numerous other applications. So high-level compiler transformations have been used for loop vectorization, which was one of the first goals of high-level transformations. Today, vectorization techniques are found in practically all compilers. Loop tiling, used to enhance locality. Automatic insertion of message passing operations in shared memory and global address space program. Insertion of statements to instrument programs or enable functionality. And translation of formulas into code, as has been used in auto-tuning systems like FFTW and Spiral. And in this case, you will need to complement traditional compiler techniques with computer algebra methods. There are other applications that remain in the domain of academic research, but they still are very important. One is translation from dense form of computation into sparse forms, and translation of recursive computation into iterative computations, and after that, parallelization of recursive computation by parallelizing the iterative computations. There are, of course, many other uses of high-level compiler transformations, and the number of applications continues to increase with the introduction of new languages and machine features. So high-level source-to-source transformation were introduced several years after the first compilers of the 1950s. From what I know, the early compilers of the 1950s used high-level transformations on a limited basis or not at all. The first paper on the subject that I know of is that by Allen and Koch in 1972. High-level compiler transformations were therefore introduced quite early in the history of computing, earlier than 1972, since papers usually lack the work. In the 1972 paper, Allen and Koch present a short catalog of high-level transformations, including procedure integration, loop unrolling, and loop fusion. Other early papers describe a source-to-source preprocessor known as the parallelism that translated sequential Fortran programs into a parallel Fortran dialect for ILIAC 4 called IVTran or Fortran, depending on how much one likes numerical Roman numerals. The paper by Lohmann contains an extensive collection of transformations used by the parallelism to enable or improve the quality of vectorization. In the paper on the parallelism, they describe vectorization and the famous hyperplane method. So the hyperplane method, in case you haven't heard of it, is illustrated here using this example extracted directly from the parallelism paper. It transforms a multiply nested loop, doubly nested in this case, so that vector operations could be executed along the diagonals of the iteration space. Here is the list of transformations described in these three papers. In the paper by Allen and Koch, the paper on the parallelism, and in the paper by Lohmann. This is a long list of transformations, most of which are still used today, 50 years later. Indeed, the transformations in this list have had a greater longevity than the transformations implemented in the first Fortran compiler. An important transformation that is not in this list is tiling, which was introduced around 1980. Now, a weakness of these early descriptions was the absence of a powerful mechanism to check when it's correct to apply each transformation. In the case of fusion, the Allen-Koch paper presents a very simple correctness rule, that the computations in either loop do not depend on the computation of the other. And in the paper by Lohmann, the criterion for fusion is that two loops could be vectorized. A more advanced methodology to check for correctness was developed at Illinois based on the notion of data dependence. The earliest document describing this work is the 1971 Yoichi Muraoka's PhD thesis. The notion of data dependence has had a profound influence on the development of high-level compiler transformations. It enabled the creation of sophisticated transformations by providing a more accurate correctness checking mechanism than the intuitive methods just described. Let us see an illustration of how data dependence analysis is used. Consider again loop fusion. These two loops may be fused despite not being data independent from each other and the second loop not being vectorizable. So it is easy to see by manually checking the result that this will be correct. This will be correct to carry out the fusion despite these loops not meeting the criteria just stated. The way dependence analysis determines that two loops cannot be fused is by checking if a new backward dependence arises after fusion, as is the case in these two loops, which cannot be fused due to the reversal of a dependent as shown here. As we can see in this case, data dependence gives us a simple criterion for fusion, namely that those dependencies are reversed and a similar situation arises in other transformations. Their ability to provide simple criteria for correctness is the reason why data dependence analysis has been crucial to the success of some of the most important high-level compiler transformations. So the study of high-level compiler transformation has been an active area of research since their introduction. The literature on the subject is quite extensive and continues to this day. Although the community is relatively small when compared with that of some applications domain like computer graphics or machine learning, there are still too many influential contributors for me to mention all of them in this very short summary. So at the risk of being unfair, I'll mention 3 groups that, in my opinion, made the most significant contribution. First is the group of David Cook at Illinois, where I did my graduate studies. The group of Ken Kennedy at Rice, and the community of researchers that developed the polyhedral model, which include Utpal Banerjee, Chris Lengauer, Paul Fautrier, and Albert Cohen. One of Kennedy's contributions is one of the best books describing high-level compiler transformations that he co-authored with Randy Allen. So we now ask, what is the legacy of several decades of work in this area? Well, first it gave us an extensive catalog of program transformations that form a true program algebra that can be applied by hand or automatically. It gave us a technology that can target a wide range of machine classes. These machines can contain one or more parallel features, such as instruction-level parallelism, vector operations, multi-cores, GPUs, and even clusters. Finally, it had a profound impact on compiler technology, to the point that today high-level compiler transformations are found in practically all C and Fortran compilers. But despite all these influential contributions, there are some important open problems. One is identifying the limits of the transformation approach. In other words, we wonder how far can we go by applying transformations. For example, as we just showed, we can transform row by row matrix transposition into transposition by submatrices, just by applying tiling. The same can be said of transforming row by column matrix multiplication into multiplication by submatrices. The question is, what classes of algorithms can be derived from others by applying transformations? For example, can Strassen's algorithm be derived automatically from the basic matrix multiplication in the form of a triply nested loop? Second, also very important, is the need for a methodology for compiler implementation, including a methodology to write optimization reports that are notoriously misleading in today's compilers, as well as for deciding the order in which transformations should be applied. While we understand syntactic analysis well and have a powerful program algebra, the optimization process remains poorly understood and is today a great challenge for compiler technology that is yet to be effectively addressed. Sometimes compilers produce misleading optimization reports and fail to apply even simple transformations. This hinders the effectiveness of compilers as optimization tools. So what are the consequences of this lack of powerful optimization methods? A first consequence is that transformations of the source program could significantly impact the quality of the resulting code. We illustrate this next with 2 experiments we did. The first experiment was a study on the effectiveness of vectorization by ICC, GCC, and XLC, the Intel, GCC, and the IBM compilers that we did several years ago, but whose results, I believe, are still valid today. The experiment used a modified version of a collection of loops created by Dongarra and his co-workers in the late 1980s to evaluate vectorization. One of the main results is that in approximately 30% of the cases, both the IBM and the Intel compilers were able to vectorize only after the program was manually transformed. All the high-level transformations that we manually applied could have been applied by the compiler. They are listed in this table. The fact that they were not applied by the compiler is a clear manifestation of the limitations of today's technology. The second experiment evaluates compiler stability. We say that the compiler is stable if it delivers the same performance for codes obtained by high-level compiler transformations. For example, a stable compiler should deliver the same performance for these two loops that only differ because their loop headers are interchanged. We believe lack of stability is a symptom of the lack of a powerful optimization methodology. A truly effective compiler should be stable. That is, should be able to change all versions of a code obtained by applying automatable transformations into the best version. For our study on stability, we use about 1,000 loops extracted from a variety of well-known benchmarks. The different versions generated for each loop were obtained by applying subsets of the following two sequences of transformations. Each transformation in these sequences was applied in multiple ways. For example, unrolling was done twice, 3 times, 4 times, and so on. And similarly for the other transformations in the sequence. This process generated multiple versions for each loop in the collection. The results obtained are shown in this graph. Here we plot for 3 different compilers the ratio of execution time between the fastest and the slowest version. For the graph, we order the loops by increasing execution time ratio for each compiler separately. What this graph shows is that for numerous loops in our collection, compilers do not exhibit stability. The performance ratio between versions can be up to an order of magnitude and more. The limitation of the technology not only causes instability within a compiler by delivering different performances across program versions, but also causes instability across compilers. Thus, a second consequence of the limitations is that different compilers deliver different results for the same code. This is not difficult to believe. We have observed that no compiler is the best in all cases, and that the performance difference between code generated by different compilers can be significant. In particular, in the vectorization study mentioned above, we found that some loops were vectorized by some compilers and not by the others. And we did not find a way to predict which loops will be vectorized and which will need manual transformations to enable vectorization by each of the compilers. Also, in the paper, The Rise and Fall of High-Performance Fortran, Kennedy and his co-workers gave the following as one of the difficulties they face. That is that different vendors focus on different optimizations in their implementation, causing a single HPF application to deliver dramatically different performances on machines from different vendors. We can try to reduce the impact of instability. The goal is to reduce instability to improve the quality of compilation, which typically means faster object code. To reduce cross-compiler instability, we could use multiple compilers and select the best code generated by them. We could even translate each part of the program in different ways with different compilers and combine results to form the final object code. To reduce intra-compiler instability, we could transform the program in multiple ways, searching for an optimal solution. The idea is to create a space of versions from which we will search for the best one. Using multiple compilers is the approach of the meta-compiler or M-compiler developed at UC Irvine by Wiedenbaum and his co-workers. The M-compiler proceeds as follows. First, it partitions the program into multiple functions, some obtained by transforming the program. Each function is translated in multiple ways using different compilers. And the fastest version of each function is selected to create the final object code. As can be seen in this graph, this approach can produce significant speed-ups over compiling everything with just ICC. Now let's talk about an approach to reduce the effect of intra-compiler instability implemented in a system called Locus, developed by Thiago Teixeira for his PhD thesis. The idea is to automatically transform the source program, which we call the baseline program, in multiple ways. These different versions form a space of versions. Then, this space is empirically searched for the fastest version. That is, execution time of each version is obtained by actually executing the code in the target machine. As is typical in auto-tuning systems, the space of versions could be immense. Therefore, it's desirable to give programmers control over the size of the space of versions. To this end, programmers are given a language to control which transformations are applied and in which order. Here is a program in the Locus language to control the transformation process. The program includes pragmas to label the target of the transformation, in this case a triple nested loop implementing matrix-matrix multiplication, statements to indicate which implementation is to be used to apply the high-level transformations. In this case, it's the well-known Rose system developed by Dan Williams and his co-workers at Lawrence Livermore. And finally, the language also includes statements that indicate which operations are to be applied to each labeled statement in the baseline program. In this case, we're requesting that both tiling 2D and tiling 3D defined above be applied to the loop labeled matmul, and that when tile 2D is applied, the innermost loop be on roll. The use of empirical search and the customization of the transformations applied give Locus advantages over conventional approaches. This is illustrated using a matrix-matrix multiplication implementation, which was transformed in multiple ways. The result is shown in this graph, where we can see that the code obtained from Locus outperforms MKL and Pluto in some cases. Work on Locus continues in the Quality as a Service project. This is a project put together by David Cook, which involves researchers from multiple institutions, including Intel, UC Irvine, Illinois, and the University of Versailles. The goal of QASS is to develop a tool to facilitate selection for each program of an optimal machine, a software system, and a collection of transformations. And if you are interested, you can find information in this website. Well, to conclude, after more than 50 years, progress in high-level compiler transformation have been impressive. And although work continues in the development of analysis and transformation techniques, the great open question of compiler optimization methodology remains an open problem. The incorporation into compilers of auto-tuning search strategies similar to those used by Locus is a possible direction. But I don't expect this to be the whole answer. Most innovation is needed. This is a fertile area for future research, although there are few low-hanging fruits in this field. Thank you.
Thank you very much, Professor Padua, for that wonderful talk. We have time for maybe one or two questions from the audience for Professor Padua. Please use the microphones that are in the aisles.
Thank you. Hi, Professor Padua.
Hi.
This is Valerie Taylor at
Hi, how are you?
Hi, and congratulations on the
thank you
award.
very much.
I really enjoyed your talk and looking at, over the years, the impressive contributions in terms of compilers. And I would welcome your thoughts, let me go back. I would welcome your thoughts on, let's say, the next 10 years or the next decade in terms of open challenges. I think especially, let's say, looking at energy efficiency, in addition to looking at execution time.
Thank you. So I think there are a number of topics to work on. In the area of transformations themselves, I think the work on high-performance Fortran remains unfinished. We really need more powerful strategies to generate automatically code that will execute and perform well on clusters, starting from easy to read and maintain code. And also we'll need to do more work in the area of taking code and targeting the same code to a variety of target machines, from GPUs, clusters of GPUs, vector units, and so on. So that's one possible direction. And the other is what I was saying. We really need to understand better how to write compilers so that they are useful optimization tools. Today, compilers are very hard to use. They give misleading reports, and in many cases, they fail to optimize, forcing the programmer to first having perhaps to look at the assembly code because it's not clear what the compiler did for them, and then apply transformations in a search for an optimal version of the program. So there is a lot of work that needs to be done there. Part of the problem for me is that those are no longer low-hanging fruits. Those are difficult problems. And the community, the compiler community is relatively small compared to the other things that are going on today.
I think in the interest of time, we'll have to stop the questions there. I apologize to those of you who had questions. Hopefully you'll be able to find Professor Padua after this talk. So let's thank Professor Padua again.